Thank you very much, everybody, for being here this afternoon. Thank you so much to our guest speaker, Kostas. Welcome. Very nice to meet you. And thank you for giving this presentation. I'm going to hand over now to Prof. Andronikos to please do the introduction. And again, welcome to our attendees. Thank you for being here today. Andronikos, over to you.
Hello to everyone. Good evening. It's a pleasure to have here a colleague, Konstantinos Dialektopoulos, Dr. Dialektopoulos. He graduated from the University of Creta in Greece. He did his PhD in the University Federico II in Naples in 2018. And since then, he has been in various institutes doing research. This period, now he's located in Malta, in the University of Malta. And he's a cosmologist, he's a theoretical astrophysicist, and today he will talk to us about new techniques techniques for the data analysis which can be applied in the study of cosmology. So, Konstantinos, please, you can start.
Yeah. Thank you very much, everyone, for being here. Thanks, Andronikos, for the very nice invitation. Yeah, I'm a researcher at the University of Malta. And today I'll try to talk about the progress that we did last couple of years on reconstruction techniques using like Gaussian processes, neural networks, and stuff like that. But before I do that, so I'll try to motivate a bit the field, let's say, of research. So I'll start, with the reasons that we need to do what we do. Then I'll talk about parametric reconstructions a bit. So what kind of reconstruction techniques there are in the literature. I split them into two, parametric and non-parametric ones. I'll focus mostly, as I said, on Gaussian processes and artificial neural networks. And then I'll talk about what we can do with the results that we extract from these processes. Okay. So yeah, we all know that the concordance model in cosmology is lambda CDM, with lambda being associated usually with dark energy and cold dark matter, CDM being cold dark matter, which is like a non-interacting form of exotic matter. Now, this model, apart from its great success in many observational tests, it possesses also some inconsistencies. And also, the last few years, with the advent of technology, these inconsistencies become more and more statistically significant. And of course, these are called cosmological tensions. So what is a cosmological tension? Is a discrepancy, let's say, between two measurements of two of the same cosmological parameter. So imagine you measure, let's say, the height of a building with a laser and with a measuring tape, and you find a discrepancy between the two measurements. This is exactly the same what happens in when we try to measure, for example, the expansion of the universe using local sources and faraway sources from the CMB. Two of the most significant ones, let's say, statistically significant tensions are the H0 tension and the sigma 8 tension, S8. The first one describes of course, the expansion rate of the universe using different measurements, like local measurements from Cepheids and supernovae. We find H0 to be around 73 kilometers per second per megaparsec, while when we use cosmic microwave background data from Planck, for example, the latest ones, we find it to be at around 67, and there is a discrepancy between these two values around 5 sigma. And of course, this suggests either that unknown systematic errors exist in our measurements or in our instruments, let's say, or we should look for some new physics. So there are several discussions about early dark energy, modified gravity, and several remedies, let's say, to this tension. The S8 tension refers to the growth of structure. So the S8 parameter measures the clustering of matter in the universe, and large-scale structure surveys like weak lensing surveys, galaxy clustering, and so on, suggest less structure formation in the early universe than predicted by lambda CDM and CMB data. And of course, either there is new physics in the dark matter or dark energy sectors, or there is some modification of gravity there, if there are no systematics, of course, in the measurements. Apart from these, there are less statistically significant tensions as well. So even as early as from Kobe or WMAP in the CMB, we noticed some anisotropy anomalies. So we found some deviations from Gaussian fluctuations and statistical homogeneity and isotropy in ΛCDM. Of course, there are some suggested remedies like closed universe or different ones, but none of them are, let's say, convincing enough. There are cosmic dipoles where there have been studies suggesting violations of the isotropy of the universe. There are missing satellites, so around the Milky Way, we should be able to see some like 500 more or less dwarf galaxies, but what we see is only about 30, I think. So it's at least an order of magnitude less. There are some problems with the density profile of dark matter. Simulations show different things than what we observe. There are baryonic Talley-Fisher relations. So dark matter and baryonic matter should not, let's say, interact with each other or should not evolve in the same way, but we observe different things with baryonic Talley-Fisher relations for galaxies. Okay, yeah, this is in greater detail the H-naught tension. You see that Planck mission from CMB and the DES survey, DES find some 67.4 kilometers per second per megaparsec, while local measurements like late time measurements show around 74, which are the extreme ones. Of course, there are some values in between using TRGBs and several others. Here I show the evolution, let's say, of the measurements throughout the years. So you can see that we started measuring in the early 2000s from local. The orange ones are the local measurements from supernova and Cepheids, while the purple ones, magenta, are the ΛCDM, the CMB measurements. And you see, I mean, the uncertainty becomes less and less as we approach today. So this difference between the two measurements is today at around 5 sigma. The same holds for sigma 8. It's not that significant statistically yet, but it's around 3.5 sigma. So these blue ones are the CMB measurements, while all the rest are like weak lensing, galaxy clustering surveys, cosmic chronometers, and several others, which show a bit less clustering, let's say, in the early universe. So yeah, if these tensions persist, they may indicate, let's say, the need for new physics beyond ΛCDM. And there are approaches, possible explanations, let's say, in the literature, including early dark energy, modified gravity, or of course, there are people who believe that there might be systematic errors, like undetected issues, let's say, in the measurement techniques. So yeah, what are the reconstruction techniques in cosmology? So the reconstruction techniques have become crucial for understanding the phenomenology of dark energy, the expansion history, and also the growth of large-scale structures. And they aim to capture specific features or general trends in the data, to test a predefined physical model against observations, or explore theory agnostic, let's say, framework to elucidate the phenomenology of cosmological functions. So in general, reconstructions can be categorized into two, let's say, there are two main approaches, the parametric and the non-parametric ones. So the parametric ones, they impose an explicit form on the function being reconstructed, and thus it reduces the uncertainty in the result. However, of course, the a priori assumption of a specific model, it limits the flexibility, let's say, of the reconstruction and introduces biases regarding the properties of the cosmological functions of interest. And in order to mitigate this, we use some non-parametric reconstruction methods, which, I mean, they use theory agnostic frameworks. And they are particularly useful for gaining insights into the dynamics of cosmological functions when the true, let's say, underlying function is not directly observable, but it can be inferred from observed data. Okay. I split. So based on the white paper we wrote recently in a cost action I'm part of, I used the classification we did there. And I split the parametric reconstruction in three parts: the phenomenological ones, the physically motivated ones, and the model dependent ones. So the phenomenological parameterizations, they focus on capturing specific behaviors, which means like to test whether certain trends, like evolving equations of state, deviations from general relativity, modified growth of structure, and these kind of trends. They try to test if these trends are compatible with observational data. So one very well-known example is the go-to, let's say, Chevalier-Polar-Cylinder parameterization, which suggests that there is a dynamic, let's say, behavior in dark energy. So the DESI collaboration, for example, recently employed this parameterization in the analysis of year 1 and year 2 BAO data, baryon acoustic oscillations. And they found evidence suggesting that there is a preference, let's say, for dynamical dark energy with statistical significance of 2.5 sigma. Another one, which is a modification of the CPL, is the JBP. And this is designed to exhibit different behaviors at larger redshifts, as you can see here from the denominator. There are several, actually. The dark energy, dark matter interaction. So with this parameter psi governing the strength of the interaction, it is proposed as a way to represent, let's say, the interaction as a function of time with this Hubble function here, and the energy density of dark matter. And of course, since this is purely phenomenological, it can also be extended and include dark energy here as well. There are several more, like parametric forms for dark energy, like X of Z, growth rate parameterizations, gravitational slip, where you measure the ratio of the Newtonian potentials, and so on. But of course, these phenomenological parameterizations allow for broad exploration of deviations from the standard model without committing to a specific underlying theory. The physically motivated ones are derived from fundamental theories and ensure consistency with known physics. So these models are often constructed from Lagrangian formulations, so field equations, let's say, or we just take extensions of GR, which is the easiest thing to do, let's say, instead of changing geometry or doing something very exotic, let's say. And then, of course, this ensures that theoretical principles like energy conditions, stability constraints, and stuff like that are satisfied. Of course, one of them, the easiest one, you can see it's quintessence. So you have like a scalar field, which is time dependent. I mean, if you do cosmology, it's just time dependent. It inherits the isometry of the metric. And then you construct, let's say, the equation of state parameter of this theory, which is this ratio here. And it has the peculiarity, let's say, of behaving like W is greater than -1, which holds in λCDM. Of course, if the scalar field is phantom, then it could be also less than -1. And there are extensions to it as well. So if you consider like self-interactions of the scalar field, you have like K essence. If you consider all the most general, let's say, scalar tensor theory, you can do the same thing in Horndeski, and it has been done in the literature. F of R theory, dark matter models, whatever. I mean, warm dark matter models where like a non-zero velocity dispersion modifies the matter power spectrum, self-interaction dark matter, several things you can do with physically motivated parameterizations. But now both phenomenological and physically motivated parameterizations, they aim to describe the evolution of cosmic components and test deviations from λCDM. the phenomenological parameterizations provide a flexible way to analyze trends, while the physically motivated ones ensure the consistency with fundamental physics. There is a third way, the so-called model-independent parameterizations. And I mean, this difference, because they differs from the previous ones, because they inherently require assumptions about the functional form. So there are several model-independent parameterizations. You can the most used one is the basis representation parameterization, which provides a flexible and systematic way to reconstruct cosmological functions by expanding them in terms of a chosen set of bases like Taylor, Fourier, Padet, and so on. There are several interpolating methods where positions are defined and then connected in a specific manner with the chosen connection method determining the type of interpolation used. I mean, these positions act as free parameters whose optimal values are determined through Bayesian iterations, Bayesian parameter inference, like MC or nested algorithms. And then you can reconstruct your cosmological parameters. And of course, there are the cosmographic parameterizations as well, which is like expanding the cosmological parameters around z equals 0. There are several issues there. Many people claim that they are not very well behaved in for large redshifts, and that might be true. But there are recent studies by Matt Visser and collaborators, Jessica Santiago and several others, that claim the validity of cosmographic parameterizations up to z equal 9 if you use different than Taylor expansions. Okay. Non-parametric reconstructions. I just wanted to show you what parametric ones are. I didn't work, to be honest, with these, even though I've read a lot and many people use them. I work mostly on non-parametric ones, and these are data-driven methods that do not rely on any specific functional form of the reconstructed function. So what they do is they try to minimize the model assumptions. The aim is to describe the data without imposing any strong a priori constraints. And the most common one, I think, is the Gaussian processes, but there are, of course, others which, they grow in popularity the last few years, which include artificial neural networks, iterative smoothing methods, lowest plus CMEX, which are parametric regressions for trend analysis. There are several ones. Let me focus on some of them. So the most popular one, as I said, is Gaussian processes. So the idea behind Gaussian processes is to try and assume that when we get data from experiments or from observations, to try and take those as estimators of Gaussian distributions, and from there to try and learn how to reconstruct the whole diagram, the whole parameter, let's say, in the region that we want to reconstruct it. So just imagine here we have some data points. If we look at these graphs, we can see that the dotted line, let's say here, represents the true value in this in the left panel. But the problem, here we can get the best fit using whatever best fit we want to use, like polynomial, exponential. Just by looking at the data, we can assume a specific form that the data might have. But the problem with this best fit is that as soon as we choose some function, we're putting in some physical parameters, right? So we say that our model must behave in a certain way. And the problem with that is that if I add like an extra data point in the plot, it's not necessarily the case that this is still the best fit, and also that it will remain, it will behave actually as the true values do. So the target of Gaussian processes is to sort of learn the behavior of these data points. So if I had to give like a proper definition of Gaussian processes, it would be that it's a stochastic process where any finite subset of my data is assumed to be a normally distributed around the mean mu. and is described by the so-called covariance function or kernel, which what it does is just correlate the data points with each other. So yeah, as I say here, mu in cosmology is usually considered to be 0 without loss of generality, even though there are studies which suggest that we should maybe use different ones. But what's mostly used in the literature is just the mean function is 0, and then the covariance function can be used to learn the behavior that is produced by the data points. Okay, so since in cosmology we have, the cosmological parameters are usually continuous functions, like the Hubble, for example. We do regression, even though Gaussian processes can be used for classification as well. And what we do, we should have a model in some way, let's say, and the model here is inserted through statistics. So we have in the kernel, in the covariance matrix, we have some theta hyperparameters, which are statistical parameters and describe the data points with each other, the correlation of the data points. So what we do is initialize them, then iterate over some values using whatever method we want, like MCMC or whatever, Bayesian inference, anything that we want. And what we get in the end is like a model-independent reconstruction in the physical point of view of the behavior of the parameter that we want to reconstruct, which is of course better than a specific, let's say, fitting that we used to do before this method. Okay, let me show you an example of an application of Gaussian processes. This is very old, actually. This uses the GAP code by Marina Saikel et al. In 2012, but still it's pretty valid. So what they do here is they consider several data sets from CCs are cosmic chronometers plus supernovae, and plus in the orange one, they use also BAOs. And what they do is they reconstruct the Hubble parameter, h of z, with respect to redshift, up to redshift 2 point something, where we have the Lyman alpha data point from BAO. So you see that the blue, let's say, shaded region refers to CCs only. The green one refers to CCs plus supernovae, and the orange one, which is much more constrained, let's say, much less error bars, is the one that includes also the BAO measurements. This in the left panel doesn't include any prior, for example, at z equals 0. So you see here that there might be a bit more uncertainty for low redshifts. While here, we also use some prior. I think this uses the the RIS prior, which is the Planck one from supernovae. But of course, this has been done with other priors as well, like TRGB, BAOs, and several others. So this one that, of course, uses a specific prior, you see that the value of H naught at today is closer to the prior itself. So it is, let's say, susceptible to the choice of the prior. Now, okay, then if Gaussian processes work, then why go to other non-parametric methods? And the answer is because they have some problems themselves. One of them is the overfitting. So in small data sets, as we still have in cosmology, for example, the cosmic chronometer data set is like 32 data points. Okay, supernova the Pantheon Plus data set is now like at 1700, I think, but the previous one was around 2000, 2048, if I'm not mistaken, which is still, very small data sets to do, let's say, machine learning techniques. And the Gaussian processes, because we have small data sets, they tend to have this kind of behavior, try to overfit, let's say, the reconstructed function. They try to overdetermine the parameter that we want to reconstruct, especially in low redshifts. And also, we have some kernel selection problems. So The kernel that we introduced it by hand, and it describes, as I said before, the correlation between the different data points. And of course, this introduces some statistical bias in the analysis. The bias is not physics again. We don't include any specific physical model, cosmological model in the background, but we introduce some statistical bias. Okay, in order to tackle these problems, what we can do, we can go to different methods, and one of them is the artificial neural networks. So what we really want to do is to go on the deep, let's say, end of machine learning, and to see if it can help us solve some of the open problems in cosmology, or even construct our gravity theory solely based on the data. So what we wanted to do is have the neural networks are usually, they are motivated, of course, from biological neural networks, and they are organized in different layers. The first one is the input layer, with the data, let's say, that we input in the network. The last one is the output layer, which is the parameters that we want to reconstruct, and all the in between are several different layers with several number of neurons, which are called hidden layers. And of course, they are interconnected with each other. The neurons now are built on the so-called activation function, which governs the output of the neuron. And thus, every neuron contains a number of hyperparameters, which must be assigned a value. And to do this, the network is trained using some observational data, is optimized, and then we get the correct neural responses. So the core difference between GPs and ANNs is that GPs, Gaussian processes, entail a different supervised form of learning, meaning that the data are used concurrently as the reconstruction takes place, while ANNs are unsupervised in a sense that once the neural network is trained, it no longer requires the data to reconstruct the parameter at new redshifts, since it is already imitating, let's say, the natural process itself. So, okay, in order to build an artificial network, we need to know some properties, like how many hidden layers we need, how many neurons each layer should have, and so on. So what we do is, because the datasets we have so far are limited, what we do is try to construct some mock data, as we see here. For example, this is a gamma distribution of the cosmic chronometer data. And we use this just to get the optimal, let's say, architecture of the network. We don't use this to train the network and extract physical results. We just use this in order to get which is the optimal architecture. So how many layers, hidden layers we should have, how many neurons each layer should have, and so on. And the same we do with the uncertainties in the right part here. How can we do that? We have some specific property functions, let's say. One is the risk function, which optimizes the number of hidden layers. As you see here, we have the difference between the observed and the predicted value. And as soon as this is minimized, we get the optimal. We do the same thing for different configurations, for different architectures of the network. And as soon as this is minimized, we get the optimal one. We have the loss function as well, which is how many iterations we should do in our network in order to train it. There are several different loss functions depending on the shape of the datasets that you use. The most popular one, to be honest, is this one, the L1, which is just a pure difference between the observed and the predicted value. But if you want to use like correlated data, as we have, for example, in the cosmic chronometers or the Pantheon Plus, where we have this covariance matrix, we use this LCDM loss function, and this is how we figure out, let's say, how many iterations we should do in order to train our network. So this is exactly what we do here. So we did this thing I described like for 24 different configurations. of the network with 1, 2, and 3 hidden layers, and 2 to the n neurons, with n being from 7 to 14. And we found that one layer is optimal. So this is the output for one layer, and specifically for 2048 neurons, the risk function is minimized. So here is the risk function, and here is the number of neurons that we should have, and it's minimized for 2048 neurons. And here we have the different loss functions, where, as I said before, we use the L1 if we have non-correlated data, but we use the L-chi-square if we have correlated data. And we see that after, let's say, 1,000 iterations, more or less, it doesn't make any difference to the training of the network. So yeah, in these two papers, what we do is, I mean, these results are just reconstructions of the h of z over h naught. So yeah, as I showed before, the reconstruction of the Hubble diagram using Gaussian processes, this is exactly the same thing, but using ANNs. So on the left panel, we have the reduced Hubble parameter from Pantheon data with the correlated, let's say, loss function, while on the right panel, we have the same parameter, the reduced Hubble parameter using cosmic chronometers and BAOs. And as you can see, because Pantheon data go up to 2.2, 2.3, of course, the uncertainties above this redshift are huge, even before, to be honest, they are pretty big. While when we use BAOs, where we have also the Lyman alpha value at 2.5, I think, 2.4, if I remember correctly, the uncertainties are still a bit smaller. Okay, we use also some diagnostics in order to test if our analysis is on the right place. So we use the OM diagnostic, which serves as a null test, let's say, to distinguish between the ΛCDM model from alternative dark energy and modified gravity models. And this is defined as a fraction where E of z here is the reduced Hubble parameter that we have already reconstructed over 1 plus z cubed minus 1. And this works, let's say, on the principle that different models have different evolutionary trajectories in the z-OMZ plane. And yeah, what we do here is plot this function with the reconstructed E of z that we have, using ANNs on the left and using Gaussian processes on the right. And as we can see, even though at very low and very high redshifts, the reconstructed values are not well constrained, we see both using ANNs and GPs that the OM curves are characterized by a positive, let's say, slope above z equal 1. But nonetheless, of course, the ΛCDM model, assuming the Planck best fit, is consistent with within 2 sigma here. I mean, it's still in the error bars. Similarly, if we assume that the H naught tension is cosmological in origin, these authors here, they suggested to explore the possibility of other inferred values of H naught, predicting a running, let's say, of H naught with the redshift. Such a phenomenological, let's say, evolution of H of z with H0, sorry, with redshift is an alternative which resolves, let's say, the tension without any direct investigation of the fundamental framework. And again, our results show that the mean reconstructed H naught curves in both the figures show a non-monotonic evolution with respect to Z. Okay, this is where it becomes interesting. So apart from whatever phenomenology we can do using reconstructions, we can also use them to constrain our theories. So I included a specific example here of a Horndeski class of a specific class of Horndeski models. So as I said before, Horndeski, for those of you who don't know, is the most general, let's say, scalar tensor theory in 4 dimensions with a single scalar field that lead to second-order field equations for both the metric and the scalar field. This is the mapping to Horndeski that we used. This is called, I think, not K-Essence, but a designer Horndeski by these authors here. So G2 is just a function of x, the kinetic term of the scalar field. G3 is the same, but a different function. G4 is a constant, so we have a minimal coupling, let's say, to gravity. And G5 is 0. So the action assumes this form. We have GR minus a function of the kinetic term of the scalar field minus non-minimal interaction of G times box phi, which is like a K-essence, let's say, but with a kinetic term here. We express the cosmological equations in a form where we have on the left-hand side some unknown functions, k of x in this case, and g, the derivative of x with respect to x. And then on the right-hand side, we have already known or reconstructed, let's say, functions from the neural networks that we use. And what we find is that x, the kinetic term of the scalar field, as a function of z, it should be reducing. K, the function, the coupling, the kinetic term, let's say, the kinetic function of the scalar field in the action as a function of redshift should be increasing. K as a function of x, now it should be decreasing. And then the same happens for the derivative of g. So in a sense, we can constrain the free parameters, the free potentials, let's say, of the theory just based on the reconstructions that we did using purely observational data. We can go on, of course, and construct, as I said before, the equation of state parameter, dark energy equation of state parameter in this specific theory, which takes this form here, the fraction, this fraction here, where we have all these parameters reconstructed already. So we can see, we can plot it and see its deviation, let's say, especially above z equal 1 from lambda CDM. Okay, yeah, we do the same thing here. Let me not get into these details. I mean, this is just the arctan of 1 plus the equation of state parameter, which shows exactly the same thing. Yeah, a bit about the data sets we used. So, yeah, we used, as I said before, the Pantheon plus the supernova data sets, which are 1701 light curves from 1550 supernova, and they span up to Z redshift 2.3. We also used 32 H of Z measurements, which are like they measure the cosmic chronometers, they measure the differential aging of galaxies. So these are purely, let's say, model independent measurements of H of Z, but they are very, I mean, the data set is very small with only 32 data points. Okay, I'm not sure if I should get into technical details, but okay, the process is like this. We split the data set into some 70% training and then 30% validation sets. We train the network and then we test it with the rest of the data set to see if it did correctly, if it's trained correctly. Then in order to incorporate the covariance matrix, as I said, with the Pantheon plus data, we have to minimize the chi-square loss function. And using the Pantheon data set, the optimal network now is with 2 hidden layers instead of 1 most of the time. So the goal here, the aim was to see if the H0 tension could be described not as a Hubble tension anymore, but as a tension in the absolute magnitude of supernova, in this MB value here. So at first, we wanted, first of all, to find a value for MB, having all these data points I showed you. And second, we wanted to test if there might be a specific transition at some redshift that could explain, let's say, this tension in MB now instead of H0. So we did some math here in order to be able to express the tension as a tension in MB instead of H of Z. We reconstructed it. So this is the apparent magnitude using the Pantheon dataset at the CC cosmic chronometer data points. And we did the same thing using MCMC for the derivative of M. And what we find here in the last line is very consistent actually with the rest of the literature. So, okay, let me show you this whisker plot, which summarizes it better. So in our work, we found the value of MB being at minus 19.353, which is actually consistent with the rest of most of the literature actually, especially the ones that use the same data sets. You can see, for example, studies that use BAOs, of course, they have smaller uncertainties, but we didn't want to use it because it might introduce some, let's say, fiducial, it assumes some fiducial cosmological model in the background, and we wanted to be as model independent as possible. So yeah, our next question is MB evolving somehow with redshift? And in order to do that, to study that, we consider two types of binning methods applied to the H of Z data that we have. So the first binning method is the so-called cumulative binning technique, in which each next redshift bin has one more high redshift H of Z data point with respect to the previous redshift bin. So you see here that around Z equal 1, there might be a transition in the value of MB. So in order to be able to run the MCMC analysis in this first technique, we considered the first 6 low redshift H of Z data points up to Z equal 1.19, if I remember correctly. And then these are the derived values of MB. On the right panel here, what we did is consider the so-called redshift layer binning with a mean Z. So each layer here has a mean redshift Z bar, and each bin contains the same amount of data points. From the outcomes, it should be remarked, let's say, that there is an indication of transition of the MB at around Z equal 1, as it can be seen from both binning techniques, binning methods. And yeah, I think it is statistically significant because both different binning methods show the same result. But to me, to be honest, yeah, Z equal 1 is like next to us. So if this happens, we should have some astrophysical evidence for it as well. So I'm not sure how physically convincing, let's say, this is. Okay, we also try to do several other things with ANNs. So in this paper here and in one upcoming, we try to calibrate the 2D and 3D dynamic relations. So these are some relations using GRB data sets, gamma ray bursts. And we try to calibrate the 2D and 3D parameters of these relations using ANNs. I mean, why we want to do that is because we know that Pantheon Plus or CCs, they go up to redshift like 2.3, 2.5 to the best, in the best case scenario. But GRBs can go up to Z equal 9, so redshift equal 9. And this could help us extend, let's say, the cosmic ladder to higher redshifts and thus reconstruct also our cosmological parameters. Okay, so yeah, as a couple of final slides, the take-home message, I mean, cosmological tensions are there. So either they are systematics or new physics. We have to acknowledge them and try to see how they can be resolved. And reconstruction techniques can help us towards this way to probe, let's say, the cosmic evolution. Especially using non-parametric ones, we can do that without assuming any physical cosmological model in the background and test, let's say, all the plethora of cosmological and not only alternative theories of gravity in the literature. And yeah, I mean, I don't want to be tiring, so I'll just leave this here. Thank you very much for the opportunity.
Okay, now I should say let's thank the speaker, but we are online. Thank you a lot, Kostas. Okay, there are some thanks I can see on Zoom. Thank you a lot for your wonderful talk, and you were really on time, exactly on time. Congratulations. So, is there any question from the audience?
There is a hand. I saw a hand.
See a hand. No, this were thanks. Any question from someone? You okay? It seems that I should ask then. Okay. There's no any question.
If anybody just indicate, we can give you possibility, allow you to talk. So please, if you have any comments, please feel very welcome to ask questions, make contributions. Welcome.
Rene, can you hear me? Everyone?
Yes, hi.
Yeah.
Yeah. Thanks, Konstantinos, for the interesting talk. I think an interesting approach of trying to look at this tension issues with reconstructing functionals from the data. And do you think there is any promise in resolving the tension issues using this technique anytime soon? And how far are we in that?
Any promise you said? Sorry?
Of resolving the tensions.
I mean, yeah,
Using
that's a great
this
question,
approach,
actually.
that is. Yeah.
Well, to be honest, the most significant, statistically significant one is the H0 one, which is around 5 sigma. And I mean, the community is torn, let's say, between these two measurements, especially the shoes one from Rees et al. And the CMB from Planck. However, there are some huge groups like Wendy Friedman's group, for example, which they use TRGBs, tip of the red giant branch, and several data sets, to be honest, from JWST and from previous telescopes as well. And they claim to have found a value at around 70, which is exactly between the other two. However, assuming that they are there, they are physical and they are there, I think we should increase our significance for the rest of them as well. So for sigma 8 and for others. Now, if the solution will come from the data or if it will come from theory, it's a matter of debate. I believe that the data will help us verify or distinguish or dust off whatever between the proposed theories, let's say, between the proposed remedies, like early dark energy. Is the answer around recombination? Is the answer today? Does the gravitational model change somehow in the background? Theory itself can help us with some new models, but it's the data which will somehow dictate which ones are the correct ones.
Yeah, sure. But do you see some promise in your new technique in resolving this issue?
Yeah. So sorry, Rene, you're unmuted. But okay. I think ANNs and machine learning in general can help us. These are very basic techniques that we use here in this presentation. These are simple forward, let's say, neural networks. Right now, the people use much more complicated and interconnected neural networks. as soon as we get more and more data from different sources, like gravitational waves, for example, or data from Euclid, now that we have the DESI, the year 2 from BAOs, I think this will help us a lot distinguish, either distinguish between already existing models or even construct the models from the data only.
Thanks. Very
Yeah.
interesting.
Thank you, Amare. Thank you very much for your contribution. I see we also have Anslin. Anslin, if you have any comments, there's Nigel Bishop. Hi, Nigel. Oh, sorry, Topolo, I missed this question. Topolo was asking, Kostas, if you would mind if we can have the slides. Would you mind?
Sure, yeah, I can send them.
Okay, excellent. Topolo, you have my email address. Please just mail me. I'll get it from Kostas. Thank you so much.
Renee, I have a question for
Yeah,
Costa.
please tell me.
Costa, do you believe that it's possible to, with the data that we have, to try to extract new constraints, new tests using these techniques?
New constraints on what?
I mean, okay, with the data that we have already, I mean, we have, let's say, the supernova, the CC, the BAO, and GRBs, etc. But when we have a cosmological model, we constrain, we determine the luminosity distance. So, but do you think that we can extract more information from the data and I mean, define some new functions, just that to constrain independently the cosmological models?
Yeah, so, okay. One thing is to try to manipulate the data in a way that they can give us more information. So, okay, let's say we have a measurement of the apparent magnitude of supernova. How can we get, let's say, the derivative of the apparent magnitude? We can do some MCMC analysis, or even, I mean, recently we try to avoid MCMC analysis and use some more computer, let's say, less expensive ways using neural networks. This is not so easy yet, but it will happen in the near future. So we can somehow play, I mean, reconstruct derivative parameters from the data themselves, like derivatives or re-express, let's say, as we did here in this work, h of z as mb and so on. The different thing and the more difficult thing to do is what we did here in the, okay, let me close the chat, is what we did here with the model constraint. So the difficult thing to do in very complicated theories, okay, this is also one parameter that you can constrain. This is also one parameter that you can constrain, which comes from already reconstructed functions that you have from purely data. The difficult thing to do is bring your theory, your free parameters of the theory, in such a way that they are expressed in known, let's say, parameters or reconstructed parameters, if not known. So in principle, I would say yes, it is possible. It's kind of not so easy task yet, especially for very complicated theories like Horndeski, for example. If you want to just discuss, for example, branch decay, which has like one potential or one coupling parameter, this is very doable even today.
Thank you. And I will ask you again. I will go back. I mean, you asked very well, but I want to continue the discussion. I will go in the first part of your answer. You said it's possible to determine the parameters and the derivatives of them. So, you know that I work analytically. So, can we reconstruct the dynamical system that describes these parameters?
No, this is not one-to-one correlation, right? I think there are many dynamical systems which could give this kind of behavior for the parameters.
But we can determine. I mean, we can determine constraints for these dynamical systems.
In principle, you could be able. I mean, okay, it depends on how you code things, right? So we had this idea a couple of years ago with a colleague of mine that is it possible to use neural networks in order to reconstruct the Lagrangian, let's say, of the theory. And then you go on how do you code a Lagrangian? Like, how do you tell the computer that this neuron, let's say, describes derivatives, or this neuron describes second derivatives, or then multiplication, and then you give it specific tensors, and then it has to choose from specific tensors depending on the data that you feed it with. This is a very difficult task to do, to be honest. So one idea was like to use graph theory, and from there to go to neurons and try to code them. But even, yeah, I would have the same answer for the dynamical systems themselves, because in order for the neural network to be able to give you some specific output, you have to say what kind of output you want it to give you. So you have to train it somehow with specific data, and then it will somehow prefer one from another. To just guess whatever dynamical system, new dynamical system you might have is very difficult. And I'm not even capable of thinking something that could give you this result. In principle, it might be possible, but I'm not familiar with these computational techniques so far, at least.
Thank you. Thank you a lot. So I assume that there is no other question. So let's thank the speaker again.
Thank you.
And
Thank you.
hopefully we will meet you, Kostas, one day in South Africa. And
Yeah, I hope so too. It would be nice to come back.
Thank you very much. I'd like to thank Andronikos. Thank you very much, Kostas. If any of the people that attended today maybe have any ideas of something that we can present in the future, please let us know. Maybe we can ask Kostas to do a follow-up session or whatever you might need. So please let us know. Thank you very much. Thank you for being here, and have a good weekend. Thank you.
Thank you. Thank you.
Thank you. All the best.
Thank you. Bye.
Bye.